Welcome back. I'm picking up where I left off from trying to determine fastest path between 2 points. And I want to introduce this idea of variational methods because this is what we'll use to talk about Lagrangian and these kind of things.
I'm picking up where I left off from trying to
And
determine
it
fastest
seems
path
like
between
we
2 points.
have
And I want
we are streaming and everything's kind of working out. So that's good. All right, cool. So thinking about like this idea of like if we know what path we can define, we can get from, and here I'm kind of scrolling down. So starting up at a height, in this case 1 meter up, rolling down to 0, and going across a distance of 1 meter. Question is like how fast can we get there? And like what's the fastest path to get there? And the interesting thing is that this also comes up in physics with the idea of like nature takes the path of least resistance, or it minimizes its energy along the way, because that would be the same kind of thing here of like if nature knew what the fastest path was, then sooner or later that would be the path that gets created. Okay, so let's think about this idea here of like the total time that it takes to go from the top of our curve to the bottom of the curve is this integral. So from 0 to L, going from x equals 0 to x equals L, there's some function and then it has some derivative, and then we have like that constant of 1 over 2g in there. We have the height that it actually changes. So we've got some function. T is a function of functions. That if I know what those functions are, then I can calculate t. But I need some way of figuring out like of every possible function, what is the one that I want to use. This is where variational methods come into play. So let's start taking a look at this. So we're going to start off a little abstract and then try to get back to this idea, and specifically variational calculus. So if I, actually let's call it like f bar of x is going to be some kind of f of x plus epsilon times this like phi of x, kind of like this, where again we have 1 meter out here, we have 1 meter up here. If the fastest path, what we kind of found was, at least with the parabola, it looked something like this. If that's our fastest path, then maybe there's another path like this that's not the fastest path, and the difference between these two functions, like all of this, is going to be that epsilon times that phi of x. So f of x is, this is our desired, like, oh, not that. That if we know what the exact f of x is, then we can plug that in and we minimize it. And then f bar of x is our current guess for that function. So just any of those parabolas that we have right now. And then this is some difference between, like, this is like an arbitrary So we call it like this arbitrary. So it's some function, arbitrary, but we're going to say that it's differentiable. So f bar of x minus f of x is that epsilon times 5x, or this is some kind of like delta f, where instead of, in calculus we talk about like the limit as delta x goes to dx. This is very similar. It's just now we're talking about like functions made of functions, because again our time was an integral from 0 to 1, and we'll pull it back up from 0 to L of this like square root 1 plus f prime all over 2g times h minus f and dx. So delta f is talking about small changes in f of x, like our desire. So if we're kind of starting off with the idea that we know that there is a function that defines the shortest path, like the shortest timed path, but we don't exactly know what that function is, so we'll say that there's some delta f that defines how far away we are from that ideal function. And again, we're dealing with functions of functions, which are called functionals. So this f bar of x is now, we can call it some f of x plus that delta f. And some things, because that phi of x was differentiable, we can say that, like, so here's some properties. And again, we're starting off kind of vague, but we're going to bring it back to what we're working on here. So if I take d dx of this delta f, that's the same thing as saying d dx of that epsilon times that phi of x, where epsilon was like some kind of constant, phi of x was some function of x. So this is the same as saying like epsilon times phi prime of x, or delta y prime. So a derivative of that delta f is a delta f prime. And in this case that's important because we have both f and f prime. So if I want to look at what is the total change in this t in terms of delta L, I wrote delta y, but I meant delta f. Depends on what text you're using. Sometimes we use f's, sometimes y's. And if I take, so that's one property we need. Then the other one would be integrals. So if I'm trying to take a small change, like from an integral, like y of x, let's call it f of x. So if I'm taking like what happens when there's a small change to this total integral, it's the same thing as, I don't know why I'm putting an arrow. I can say the same thing as x1, x2, delta f dx. So I can bring that delta in and out of the integral. That's true because it's differentiable like this. So we said from the beginning that we can differentiate it just like that. Okay, so now we know that t is this integral from, we'll keep it general, well, let's call it 0 to L, like this. And do we want to grab the exact thing? I'm going to leave it, so this is a function of, it's a function of x, a function of f, and a function of f prime. So function of x, f, and f prime dx. So just saying that in order to calculate this, I need to know x, f, and f prime. So now let's look at if I can get delta t, because remember this delta is the difference between our desired and our actual. So if that delta f is 0, then f of x equals that f bar of x. So there is no difference between the exact solution and our current solution. So let's say delta t is a delta, and now we've got that first integral, right? 0 to L, f of x, f, and f prime of dx. But I can bring that delta into that integral. So it's the same as saying 0 to L, delta f of x, f, f prime, dx. And then I don't need that one in there. So that's delta t. So the chain, so if I have, and here I'm saying like our t bar equal, so the current time that we have is some desired time plus that delta t. So when delta t is 0, then our calculated time is our desired time, so the shortest time in this case. This makes things a little easier because now if this delta f is 0, then delta t is 0. So we're kind of taking that big integral, and rather than trying to evaluate a whole bunch of integrals, we'll focus on just that inside thing, that delta f. So delta f is, and now we have to use some calculus, and it's calculus, but we have to keep track of those delta values too. So a df dx times delta x plus a df df, so d big F, d little f times delta f plus d big F df prime times delta f prime. All right, now this one we haven't looked at yet. We've only talked about like what to do with changes in this function, and for an independent variable like x here, this delta x has to be 0 because we can't change our boundaries. There are no small changes to going from 0 to L. It's just that's a fixed value. Like we have to go from 0 to L. So even if we said we want to go 0 to L plus delta L, that would be a different problem. Like it's something outside the scope of what we're talking about. So anytime we have these like delta x or delta t terms, those go to 0. So then we just have these two terms that delta f is the partial derivative of f with respect to f, partial of little f, partial derivative of f with respect to f prime, delta f prime. So now we have this idea that, let me get a new page. Now now we have to integrate by parts. So that delta f prime, we can turn that into some kind of delta f term so that we have the same, and maybe we'll end up with a delta f prime and a delta f, but main thing is we want to get rid of this delta f prime somehow. Okay, so integration by parts. This is, you've probably seen this. Let's do like a little note. You've probably seen like integral, what am I thinking of? Let's go here. Integration by parts. This one. This is probably the formula that you've seen before. So yeah, I was just trying to remember. Integral of u dv equals uv minus integral v du. We're going to, really what we're saying here, it ends up being the same thing. So let me just show you another way of approaching this. I guess we can call this the OG IBP, the original integration by parts. So instead, let's do this. d dx of that d, the partial of f with respect to f prime times delta f equals a d dx of df prime times delta f plus that df prime delta f prime. And where's my highlighter? There we go. This term is what I started off with. So let me solve for it. df prime times delta f prime equals d dx of df prime times delta f minus d dx df prime times that delta f. So I can take this whole term and plug it back into my original equation. So now delta f equals this df, d big F, d little f times delta f minus d dx of this d big F, df prime times delta f, and then plus a d dx of df over df prime times this delta f. And if you're looking at this, especially the first time I looked at this, I thought, well, that just made a simple problem a lot more difficult, but this does actually help us. And if you're kind of looking at this, it is the same as this integration by parts. The integral of, if I call this u, if I call this one, let me turn it back to red. If I call this u and that dv, this one becomes or I guess we're switching it around a little bit, huh? Alright, sorry. So this is, let's see, a v du and a v dv. I'm trying to remember how it flips. I think think this is my, yeah, a u dv, and then this is the change, so this is like integral of that v du, and then integral of that u dv. One of those. We might be like flipping the sign a little bit, but uv, or maybe it's that uv, sorry. Minus the uv. Anyway, you can get this equation with this same process is the main thing. Oh, don't want to delete all of that. Okay. But let's come back to this delta t definition. This delta t is the integral from 0 to L of delta f dx, which is equal to integral from 0 to L of a d dx, df df prime times delta f dx, plus integral from 0 to L of df d little f minus d dx df d little f prime, all times that delta f dx. So I'm splitting it up into two integrals because the integral of a derivative is an exact integral. So really I'm saying df df prime times that delta f is only evaluated at 0 and L. So I need a derivative, that df prime, but I only need to evaluate it at 0 and L. And really what this is telling me is like boundary conditions of my equation. So that desired f of x has to have these boundary conditions, that it's either the derivative at 0 has to be something, or f has to be specified. So delta f has to be 0 at L and 0. And really that's what we have in our case, because what we said was when x equals 0, this point has to be 1, and when x equals 1, this has to be 0. So the delta f here in both cases is 0. So really this is saying 0 minus 0. So now we're getting a little closer because delta t doesn't depend on these boundary conditions anymore. Those are satisfied. It's just this 0 to L times this df d little f minus d dx df df prime and times this delta f and dx. So really this is that delta f term, like the thing that I actually care about here. So df minus d dx delta f, and if I want this to be 0, then this one has to be 0, because again, if that delta f is 0, that means delta t is 0, which means we're at that minimum time that we're looking for, that we're either at some maximum or some minimum. In this case it would be a minimum, because we can always make the path longer and take longer time. So we're assuming that if we hit this point of delta t equals 0, we're at some inflection point, so it's got to be that minimum amount of time. Now I have not a super easy equation to solve, but I have one equation that I'm trying to solve that's a differential equation. And differential equations, those, and this one's not an ordinary differential equation, but it's a diff EQ that is solvable. And if we kind of come back to the idea that we started with of like, what function can I plug in that minimizes the time, that minimizes the amount of time that I spend traveling from top to bottom? It makes sense that we should come up with some kind of differential equation, because that's where you're specifying like what functions can exist that satisfy this kind of problem. So we took an intuitive problem of like, how do I make the minimum time path, and it turned it into an abstract math problem, but it comes back to this idea that if I want to choose a function, I need a differential equation. Okay, so now I need that f. What was f? So if I come all the way back up here, this is my f value. Let's see, do I have... thought I had a selecting tool. Nope. Right, let's just grab everything in here, copy it, paste it, and I don't need this integral. To pen. So if I look at what is df, this is going to be not a super quick form, but we can get there, right? Let's take out 1 over root 2g, get that out of there. So now we're left with a 1 plus f prime squared over h minus f, like that. So the change in big F with respect to little f is going to be should be negative 1/2, right? Or wait, really this is 1 plus f prime squared to the 1/2, and then times h minus f to the negative 1/2. So I would still have that 1 plus f prime squared to the 1/2 times negative 1, so a negative to take care of that df, the ddx of that h minus f, and then times a h minus f to the negative 3/2. And then I can get this df prime and this one should be a 2f prime times, again taking care of that first one, 1 plus f prime squared to the negative 1/2 times h minus f to the negative 1/2. Then the hard part is getting that ddx there. The dx of this df df prime equals, so now it's going to be a little wacky, but we'll get through it because I need to do chain rule 3 times because I need ddx1, ddx2, ddx3. So first I can say 2f double prime times 1 plus f prime squared to the negative 1/2 times h minus f to the negative 1/2. Oh, and you know what? I think I forgot that 1/2. So this should be a negative. Just a negative 1/2 times that. Oh, not a negative, it's positive. So 1/2 times that. And then plus, take that f prime times ddx of this whole thing, which is gonna be a little wacky. I'm trying to do this on the fly. Let me just put some notes down to myself. So it should be f prime times f double prime, because of df prime dx, and then I can take that df prime in here, and now I can say times a negative 1/2 and a 1. Oh, yeah, I also need that 2. So f prime squared, f double prime. Yeah, it gets long, but we are getting like an actual differential equation to help us define like how do we define what that function f should be. So it takes a while, but we're chopping away at it. ddf. So then we should have a negative 1/2. So this becomes a negative, divide that by 2, and then a 1 plus f prime squared, and negative 3 over 2. And all that, I still leave this h minus f to the negative 1/2 in there. I'm just going to remove this so I can do the last one. And then plus the last part is f prime 1 plus f prime squared to the negative 1/2, and then times derivative of this one, which is going to be negative, oh yeah, ddx. So here, ddx of h minus f to the negative 1/2 is a df dx times ddf h minus f to the negative 1/2. So I should have another f prime, so it'll turn this into an f prime squared, because that's what this one's doing. And now I take that ddf up here, and that, so I should have a negative sign out front now. And then the last part is h minus f to the negative 3 over 2. And divide the whole thing by 1/2, a negative 1/2. is that a negative negative? So a plus a 1/2, like that. Definitely check my work. So I'm here. I love doing math, but I definitely make mistakes here and there. So check the work, try it out yourself, see what you come up with. I'll get rid of this because that was just like a note to myself down here. And what do we end up with? We have this whole thing. Control C. And then this whole thing, this big mess. And because we started off with this idea that this has to be true. df d little f equals ddx of df d f prime. Kind of weird, but it does give us some insights. We could start kind of playing around with this. So we have a negative 3/2 here, which we could turn this into, instead of a negative, take this, bring it down here. And then a negative 1/2 and a negative 1/2 in there, negative 1/2, negative 3/2. So I'm just trying to take these, plug them in up here. So I have an f double prime over square root 1 plus f prime squared times h minus f, and then a minus f prime squared f double prime divided by that 1 plus f prime squared to the 3/2, and then a square root of h minus f, and then plus this f prime over 2, we'll say 1 divided by this square root 1 plus f prime squared, and then times h minus f to the 3/2. So we have a couple of terms coming up more than once. I think if we multiplied everything by that h minus f 3/2, we'd end up with some stuff. There is none. So deleting all that. So it gets, we end up with differential equation. It's definitely a nonlinear differential equation here. But what else can we say about it? I think for the most part, what was the trick? I know there's a trick to this. If we're trying to turn it into differential equation, main thing that we want to do is separate out this f double prime. there's some weird square roots in here. I think everything can go over a square root of h minus f. And then also square root of 1 plus f prime squared. Then I end up with 1 extra power of, in this f prime squared, this one's, I think an extra 1/2 minus 1. Kind of like that. And then equals this negative 1 plus f prime squared to the 1/2 over h minus f to the 3/2 minus 1/2 f prime squared over square root 1 plus f prime squared and h minus f to the 3/2. And then I could kind of multiply all this stuff in there and kind of make my way through it. But let's take a look at Brachistochrone solution. This is something that this Brachistochrone curve is the general solution. So there, it's the idea that like this kind of constant, almost like a constant curvature gets in there. So let's see where they come up with. So v is root 2gy, that's what we had. Cycloid, or catenary. And I was trying to see if there's like a quick shortcut where we can see shortest curve. Shortest curve is a good one. Beltrami's identity. And really, like, I went the long way to do this, but there's an extra identity that we can use, that you can use, which is some other math. But we don't have to get into, since all the functions here for the most part are like f double primes and f primes, we should be able to simplify this. But anyway, so again, how does this relate to like Lagrangian problems? Well, the idea for Lagrange is that there's kinetic energy, which we call T. There's potential energy, which we call V. I don't know why it's T and V, but that's just how we do it. And then there's action, which we call L, which is T minus V. And for the most part, kinetic energy, it can be a function of position, and it's also a function of velocity. So this is some function of, we'll call it R and V. Potential energy, for the most part, is always just a function of position, but in general, we could say that it's some function of r and v, even if that function of v is 0. So L is some function. Oh, I wrote f for both of them, but let's keep it as t and v. Some function of r and v. And technically it could be time too, right? So let's put time in there. Time, time. And here, time, position, and velocity. Now, the idea is that if I knew what the positions and velocity, if I knew what functions there were, then delta t would be 0, but there would be no once I can get that variation in, not delta t, delta L. If I can say that this least action, that nature follows this path of least action, like it's going to minimize this difference between kinetic and potential. Technically, I could say kinetic plus potential, that's the Hamiltonian version rather than the Lagrange. But here, this is the general kind of Lagrange equations. So delta L, and if I say delta L is 0, really what I'm trying to say is that over time, if I say the integral from t1 to t2 of L dt, this one should be 0, that at least if there's no external work, we can deal with external work another time, but for now, let's say there's just either kinetic or potential energy, we're not losing anything for friction or anything, but no external work, that whole thing has to be conserved. We're not getting energy or anything from anywhere like that. So I could say this delta t1 to t2 of L dt is the same thing as integral t1 t2 delta L dt. And then this delta L, this is going to be some dl dt times delta t plus a dl d capital T delta t. Well, I guess it's just functions of, let's say, dr times that delta r plus this dl delta v times delta v. And right now it's all in terms of these like vectors, but each vector is some scalar component. So let's say that our position travels along some x, like some path x, and then velocity is going to be some v, some speed along that x direction. Then it just turns into a scalar thing. Same way that I had said that x was 0, that delta t has to be 0 because I'm integrating from t1 to t2. If I'm trying to also change the function of time, then it's outside the scope. So that one has to be 0 for this method to work. So delta L. And we could say that there's an x, a y, and a z. I just want to write down like simplest version here. So now a dl dx times delta x plus dl dv times delta v. I can do integration by parts here and say d dt of dl dv times delta x is a dl dv times delta v plus a d dt of a delta L delta v times delta, like that, times that delta x, like that. again, this integration by parts, this is what I started with, and comes up in this part here. So now I can say delta L is a dl dx delta x plus a d, well, let's put this other term first. Yeah, d dt of dl dv times delta x. And really, it's that one's a minus, right? A minus, and then plus this d dt dl dv times that delta x. And when I look at this kind of t1 to t2 of this delta L dt, this is integral from that t1 to t2 of d dt dl dv, kind of delta x, plus that integral from t1 to t2 dl dx minus d dt dl dv times that delta x integrated from t1 to t2. Can't draw my, there we go. This is an exact integral that says dl dv, and whoop, there's some ugly dl dv delta x from t1 and t2. I only evaluate those at the boundaries of t1 at time 1 and time 2. So it doesn't matter what's happening to this function, this dl dv and delta x within the, like along this integral. It's only at beginning and end. So really this is specifying like the boundary, that if I know the position at time 1 and time 2, that's okay. Or maybe I know something about the chain, like the initial velocity at time 1 and time 2. So it's telling me like what are the time boundary conditions. And that one's kind of weird to think about, like time as a boundary condition. But if we were dealing with solid mechanic, like if we were looking at flexible vibrations of things, we would end up with an integral that's just specifying boundary conditions of the object. Cool. So then we end up with this final term that delta L is this dl dx minus d dt dl dv times that delta x. Delta x, we don't want delta x to be 0, we want this thing to be 0. So if that's 0, delta L is 0, and if delta L is 0, then nature has minimized it's gone through the line of least action. So all of the work, everything that happens is either kinetic or potential energy, and it bounces between the two. And this is the Lagrange equation. That d dt dl dv minus dl dx equals 0. Where t, we can plug in that where L is t minus v, but that's how we can get to that Lagrange equation. And again, this all started with this idea that we have some kind of variation to these function of functions. So they're called functionals. And we can say like, all right, let's start with some current guess. That guess has to have an error. Let's minimize the error. So we're finding a way to define the differential equations. And again, this should give us second order differential equations for defining the motion of objects. Okay, so that's what I had for today.